This video is about Lenz's law. I'm going to motivate it first using right-hand rule. The idea is that once you're comfortable with Lenz's law, then you will know how to determine the direction of the current in the loop while the loop moves through a magnetic field, or while the magnetic field is changing in the presence of the loop. So let's look at a specific case. Suppose that we have a magnet somewhere here. So there's a magnet here. Let's draw it fairly small. Here's a magnet. Blue. Well, let's draw it in black. So I'm gonna change the color here. And did I do that? Now I think I did. So let's go ahead and draw it black. There we go. Black little magnet like this. And then let's say that it has the North Pole on the top and a South Pole on the bottom. Now, that obviously implies that we have a very specific magnetic field that points up from the North Pole and down towards the South Pole. So if I were to draw it, I would draw... Well, actually, for the purposes of this example, I really want to draw something like this. There is a line of a magnetic field. Here's another one. Let's put one more here, slightly to the left, and let's put another one here that goes out farther to the left. And then you would have a magnetic field that is similar but on the bottom, and so it would sort of do something like this, where this field points towards the South Pole. Here's something like this, points towards the South Pole. Let's do another one, and let's do another one. All right, and then if you wanted to, you would extend this so that this thing actually loops all the way around and then comes back down, so you have a magnetic field that looks like that. But I don't need all of this, so I'm just going to keep what I have. You could also add magnetic field. You could draw magnetic field through the magnet itself, and you could then make this magnetic field loop around, like maybe like this. Matter of fact, that's what I'll do, because I think this will make my picture a little better. So there you have it. On the other side, you should have something symmetrical. So here's the magnetic field and another line like this. All right, so anyways, and between these lines, you have more lines. Since magnetic field is not really lines, magnetic field is present everywhere in space around this magnet. And so this is what we have. Now, suppose that, let me extend this just a little here. And so also this one. And suppose now that you take this ring. So let's take the ring that we have. Here's a metal ring. This one actually specifically is made out of copper, so it's a copper ring. Doesn't have to be copper, as long as it's made out of some conductive material, some metal, it will do. And then you take this ring, and you, well, while it sits here in a place where there's no magnetic field, or any magnetic field that might be present here, it's very insignificant, it's so small and weak. While it sits here, there is no current flowing through this loop. It just sits there. In fact, even as I move this around, there's no current in this loop either. Whether it sits or it doesn't sit, whether it moves or it doesn't move, there's no current in it. But I'm going to take this loop and I'm going to bring it, I'm going to put it right here. So it sits just like that. As long as this loop doesn't move, no charges will flow. But let me add something to it. Remember that this loop is made out of a metal, and so it's made out of atoms. And so what that means, let me get rid of something here. What that means is that I have a bunch of atoms there in that thing, and I have with these atoms, what comes with these atoms is a bunch of charges. So let's draw a bunch of charges. I have bunch of charges all over the place. In reality, it's the electrons always that move, not the protons in these metals, but we consider it conventional current anyway, so I'm just going to put pluses. So here you have positive charge here, you have positive charge here, you have positive charge everywhere. Everywhere you have an atom, you have a positive charge. There's a positive charge all the way around, and let's maybe put a few in the back. You have these positive charges all the way around this ring, and then you take this ring and you put it in the magnetic field. So now you have, by doing that, you will effectively be putting charges, all of these charges, in the magnetic field. So let's say that this ring just sits there in this magnetic field like this but it doesn't move. Well, if the ring doesn't move, then the charges in the ring don't move through the magnetic field, and therefore there's no force on it. But suppose that this ring was actually moving downwards towards the magnet, right? So we have the ring here, and then this ring somehow is falling downwards towards the magnet. While it's doing that, the charges in the ring are moving through the magnetic field. And every time you have a charge that moves through the magnetic field, there's going to be a force exerted on that charge. So let's see if we could use now the right-hand rule to figure this out. So again, remember this loop here is going to fall through the magnetic field. It's going to fall downwards. So I'm going to place this loop somewhere here. And now I'm going to, oh, hi, Anya. So, so what we have then is we have the magnetic field line here that goes like this and points in that direction. And then we have the magnetic field line here that goes through that location where the charge is, and it points in this direction. So here's the magnetic field B, and of course this magnetic field goes this way, and it just comes out here and goes here and comes out that way. Now let's indicate the velocity of these charges. So since the ring is going downwards, the charge, let's consider this charge. Do I want to do this charge? Let me see. No, I want to do the other charge. Do I want to do the other charge? Do I? Yeah, I do. So, okay, I'm going to do this charge on this side. So I'm on this side of the ring. So this charge here is moving, it's falling downwards at velocity v. Now at the same time, I have the magnetic field that points in this direction here. All right, so I have the B field, I have the velocity v, and I have a charge q that moves through this magnetic field. So let's use the right-hand rule and figure out the direction of the force on this charge. So by the right-hand rule, now let's draw it. Let's draw the hand here. So you take your right hand and you align the fingers of your right hand with the magnetic field. So you'd have to have them point like this: 1, 2, 3, 4, and then you take your thumb and you align your thumb in the direction with the direction of the velocity. So this would be it. Here's your hand. Right, and so the thumb points in the direction of the velocity. So that would be B. The fingers straightened out point in the direction of the magnetic field. So this is B. And then the force acting on this charge would be coming out of the palm of your hand. And so the force would be pointing, it would be coming out of the palm of your hand. So it would be pointing like this, where you would have 90 degrees to the surface of your palm. In other words, at this location here, there's a force acting on this charge that points in this direction, F. And that would imply that this charge can move along this ring, since there's a force pushing it. Now let's look at the other side. Let's look at this side here, where there's a charge q, then the charge q moves downwards with velocity v as the ring moves downwards. And so what I'm going to have here is, here's velocity v. And then I have the magnetic field present here. So here's the magnetic field. And then let's draw the right-hand rule for this side. Hey, Anya, come over here. Anya, come over here. Say hi to everybody. All right, so in the meantime, while Anya's coming up, let's draw the right hand. Let's draw the right hand right here. Oh, here she is. Say hi to everybody.
Hi.
Okay, thanks, Anya. I'm drawing pictures. Yeah, they're kind of boring. Yeah, your books downstairs are much more interesting. Yeah. So, all right. So what we have here is let's set up the right hand in this direction. Well, let's draw it. So what I have is, this is going to be. Okay, I see what I'm doing. So then the right hand you would draw your fingers like this. Here's one. Here's the second one. Here's the. How am I counting this thing? That's 3. That's 4, and then I have the thumb that points straight down. So this is, okay, here's my right hand. So the velocity is pointing along the thumb, and then the magnetic field points in the direction of straightened out fingers. So I'm going to put here blue vector. And then the force itself comes out of the palm of your hand. Now remember that this is the right hand. this is the right hand here. The only way this will work is if you can't use the left hand. You have to use the right hand. The only way this will work is if the force comes out of the palm of your hand. So the force would have to, let's put that here. The force starts there, goes out, and then it just goes in that direction where you have this thing being perpendicular to your hand. So you want to actually set up your hand and see it. And that implies that the force on this charge here points into the loop, if you will. And so it kind of pushes this force in that direction. And so what I have now is that there's a force acting on this charge, and it pushes it in this direction along this vector. And so let's put F here. And then there's a force acting on this charge that pushes this force in this direction. And of course, you could do something similar, walk all the way around this circle, and you would find that you have forces that point in the direction that allows these charges to flow. From the direction of these forces, you can figure out that you can see that the current would have to be this. So here's the current I. This is how the charges would have to flow. So you could use the right-hand rule to figure out in which direction the current would flow. But let's add something to this picture here. So let's look at it a little differently now. Let's take the same loop and the same magnet and redraw it and consider something else that is happening here. All right, so I have redrawn the picture on the right, and what we have is it's the same situation. That is, you have here the ring, and the ring is falling at velocity v. I'm going to put one more velocity vector on the left-hand side. So the ring is falling, and it's dragging the charges with itself downwards, and that through the magnetic field, right? So there's a magnetic field here that points upwards. And as this ring falls through the magnetic field, the charges are forced to move, and they flow, and they generate a current. And the direction of the current is, well, this is the direction of the current. We just determined it using the right-hand rule. This is the direction of the current. I'm going to put here I is in this direction. Now, let's consider this situation, and let's see that there's something novel happening here. That is, if you have a wire, and the wire points like this, and then you have a current I in it, there's going to be a magnetic field set up by this current, and you will use the other right-hand rule to determine the direction of this current. So you take the thumb of your right hand, point it in the direction of this I, and then you would curl your fingers, and this would be the direction of the magnetic field. There would just be magnetic field around that wire, right? Likewise, let's get rid of it. If you have a loop, and the loop loops around like this, and then you have a or better yet, let me draw it like this. So you have this loop that does something like this, and then let's say that the current flows in this direction. So here's current I, and then this thing goes around and comes back out like this. Then in that case, you're going to have a magnetic field set up by this current that is present in this loop. And if you were to draw it, you would take the thumb of your right hand and point it in this direction and curl your fingers, and you would realize that the magnetic field here does something like this, right? It curls like this. In other words, there's a magnetic field that points into the loop itself. And if you were somewhere over here, you'd have to draw it like that, and somewhere here you'd have to draw it like this, and somewhere over there you'd have to draw it like this, and somewhere here you'd have to draw it like this. There's a magnetic field that points into the loop, and that magnetic field is set up by the current I that you have present here. Right? This is something that you should hopefully remember from the previous lectures you've watched. So what we have here is we have a current in a loop. Now this current in a loop is forced by the fact that this loop falls downwards through the magnetic field. But we do have a current in a loop, and that's going to set up a magnetic field of its own. And so perhaps in a slightly different color, maybe I can get something to the effect of like green. Do I have green? I have green. So let's see if we could draw the magnetic field set up by this current now. And that would be pointing, let's see, so the thumb of the right hand points along the line of the current. I curl my fingers, so the magnetic field would have to point into the page, into the loop here. This would be magnetic field. So I'd have to draw it like this, pointing into the loop. Maybe another one here. That green is biting my eyes. Let's try something. Let's keep it. So so then I'm going to draw one more, and I have a magnetic field now that points into the page, or rather into the loop, which of course means that it also points out of the loop on the bottom. So it comes out of the loop on the bottom. And now you might begin to see that what you have is a green field that points in one direction. So there's a green field that points in one direction, which is downwards. And then you have this blue field that points in another direction, which is upwards. These two fields oppose. And this is sort of the concept of the Lenz's law, in that the system is going to oppose a change. And if the loop, as you see here, is falling through the magnetic field, then the current in a loop will be set up in such a way as to oppose the change. And what's happening here is that as the loop falls through the magnetic field blue B is increasing through the loop. Therefore, the loop itself is going to set up its own field that opposes that increasing magnetic field. And once you have figured out the direction of the green field, then you can figure out the direction of the current I. I think at first the right-hand rule is going to be easier for you to grasp, the right-hand rule. But then once you're comfortable with the Lenz's law, I'm going to just put L here for Lenz's law, then you'll see that this is actually faster. So anyways, so I have showed you that there is something new present here, namely the magnetic field B, green magnetic field B, that is set up by the current in this loop. So let's consider the same example, but now through the Lenz's law. So now let's consider the same example again, but this time using just Lenz's law. I'm going to state here what Lenz's law says. So Lenz's law says that the induced current I will oppose change in the magnetic flux, or a change in how the magnetic field points through the loop. And so let's see what's happening with that. That is, what you have here is the loop, and the loop is falling downwards, and as the loop falls downwards, the magnetic field through this loop is increasing. So here's the magnetic field B, points upwards through the loop, and it is increasing here. It is increasing upwards, right? So the loop falls down, the magnetic field through this loop is increasing upwards. By Lenz's law, what that means is that the loop itself is going to set up a magnetic field that opposes that change. And so that can happen only if the current I flows in this direction. And reason being is that take the thumb of your right hand and align it in the direction of this arrow, and then curl your fingers, and you will see that that gives us a magnetic field that points like this into the loop itself, and so then out downwards. And on the other side, again, the loop will oppose changing magnetic field through the loop. And since the magnetic field is increasing upwards here, the loop is going to set up its own field that points downwards. And so the current I would have to flow in this direction. That's pretty easy to see because by the right-hand rule, take the thumb of your right hand and align it in the direction of this arrow, curl your fingers, and you will see that the magnetic field set up by this current would point into the loop, opposing the blue field. So you'd have the green field set up by the current I that opposes the blue field. And that's it, that does it. This is the way you would use the Lenz's law to determine the direction of the current I. And so Lenz's law is a little faster than the right-hand rule. You can use the right-hand rule to determine the direction of the current, but it takes longer to do. It's a little faster and easier to do the Lenz's law if you understand how to use the Lenz's law. All right, so I'm going to do a few more examples of how Lenz's law is applied, but this will do for this video.